Chords and arcs are also related to the diameter of a circle. This video discusses those relationships. Our first theorem for this video is the perpendicular diameter theorem. In a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. So if segment AE is perpendicular to segment BD, then segment CD is congruent to segment CB, and arc DA is congruent to arc BA. Believe it or not, this is going to be pretty easy to prove using congruent triangles. Imagine that. So let's draw in our radii. We know that they are congruent because of the definition of a circle. A segment CO is congruent to itself by the reflexive property. Oh look, we have two right triangles, the hypotenuses are congruent, and a pair of legs is congruent. So therefore, the triangles are congruent by hypotenuse leg, and the other legs are congruent. And thus, we have bisected segment DB by definition of bisect. But wait, that's not all. Corresponding angles are also congruent. And those corresponding angles happen to be central angles of a circle. Central angles are congruent, so the arcs are congruent. And thus, by definition, we have just bisected arc BD. So as you can see, using congruent right triangles, we can prove this theorem quite easily. Our next theorem is the diameter bisecting chord theorem. So obviously you need a diameter that bisects a chord in this one. In a circle, if a diameter bisects a chord that is not a diameter, then it is perpendicular to the chord. Oh look, segment AB bisects segment BD. Therefore, segment AE is perpendicular to segment BD. Now for this one, I actually have the proof on the next page. We're going to do this proof using a paragraph proof. Now, we know that segment AE bisects segment BD. That's given to us in the theorem. So we can use the definition of segment bisector to say that point C is the midpoint of segment BD. Since it's the midpoint, it is on the perpendicular bisector of BD, by definition of perpendicular bisector. Now it's going to help to draw in our radii here, and we know that they are congruent, and so their distances are equal. So OB is equal to OD. But since O is equidistant from the endpoints of a segment, it is on the perpendicular bisector of the segment, by the converse of the perpendicular bisector theorem. Oh, wait a minute. Segment OC, therefore, is the perpendicular bisector of segment BD. And since segment OC is part of segment AE, then AE has to be perpendicular to segment BD. So again, a pretty quick and easy proof. This is a paragraph proof. If it helps you, actually create a two-column proof or a flowchart proof. Now let's talk about the Chords perpendicular bisector theorem. That says in a circle, the perpendicular bisector of a chord contains the center of the circle. So we have segment BD, and line AC is the perpendicular bisector of segment BD. That means line AC contains point O. Let's go ahead and do a walkthrough proof of this one. Here we have our original given. Let's draw in our radii. They're congruent because of the definition of a circle. And that means that point O is on the perpendicular bisector of segment DB by the converse of the perpendicular bisector theorem. And therefore, the perpendicular bisector has to contain point O. Okay, so the perpendicular bisector of a chord basically is the diameter of the circle. So let's try this. What is the radius of circle L? Round to the nearest tenth. Well, let's see. We know that segment RS is 16. It's a chord. Notice that segment JL is perpendicular to that chord, and that L is the center of the circle. So if we extend segment JL in both directions, notice what we get. It's a diameter of the circle. Oh, the diameter is perpendicular to a chord. That tells us that the diameter bisects the chord. Segment JS has to be 8. Oh, we now see a right triangle here. So we can apply the Pythagorean theorem. Segment LS, which is the radius of the circle, squared, is equal to the sum of the square of the two legs. Plugging in the numbers here, 8 squared plus 6 squared has to equal LS squared. Squaring the numbers, and then adding them together. And of course, to undo a square, we take the square root. So that tells us that LS is equal to 10. Since LS is the radius of the circle, we know that the radius of circle L is 10 units long. We didn't need to round to the nearest 10. That's kind of nice. Let's try this again. What is the length of segment RS? Again, round to the nearest tenth if necessary. So let me see here. Well, I think, judging by what we have done in previous things, that we need a radius here. But a nice thing about this radius, segment LS, is it happens to be the same as the radius segment LP. All radii are congruent. Once again, we know that if we extend segment JL, we'll get a diameter. So JL is going to be the perpendicular bisector of segment RS. And we have a right triangle, so the Pythagorean theorem applies. Plugging in our values and squaring them. Now we'll subtract 25 square centimeters from both sides of the equation. And of course, to undo a square, we take the square root. So segment JS is going to be about 14 and 142 thousandths. I'm not actually rounding that, I'm keeping that value in my calculator so that when I double it, because segment RS has been bisected by segment JL, we can see that RS is going to be approximately 28 3/10 centimeters. These theorems are easy to apply. All that we need to do is realize that the center of the circle is contained within the diameter and then use the Pythagorean theorem.